Okay, welcome to my super cool, super fun, awesome review video. Today I'm going to be talking about isomers. And these are the book sections that talk about isomers. So, without further ado, let's get to it. Okay, so first, what is an isomer? Let me move my little screen thingy. Okay, so an isomer is a compound with the same chemical formula, but a different structure. So, for example, we've got butane and isobutane. You can see these have the same chemical formula, but the structures are different. So like they're connected in different places. And then ethanol and dimethyl ether, the molecular formula is the same for both of them, but they're connected in different places. So those are just two possible examples of isomers. And there are a lot. There are two different kinds of isomers, constitutional isomers, which have like three different kinds. There's three different kinds of constitutional isomers, and then stereoisomers, and there are two different kinds of stereoisomers. So constitutional isomers, also known as structural isomers. One second. Let me get my notes. And my little screen again. Okay, so the three different kinds of constitutional or structural isomers are chain isomers, and those are molecules with a different arrangement of the carbon skeleton. Positional isomers, and those are molecules that have the same functional group, but it's bonded to a different carbon. And then functional isomers, and those ones have different functional groups. Okay, so chain isomers, which we have right here. This is an example of chain isomers, sorry. So you can see they would have the same chemical formula, but they are bonded differently, so that makes them an isomer. And then the carbons are what's arranged differently. So like this one is just a different shape than that one. So they have a different arrangement of carbon skeletons. And then these are positional isomers. So you can see that the bromine is the functional group, but in this structure, it's bonded to this carbon, and then this structure, it's bonded to this carbon. So again, same molecular formula, different structure, because the functional group, which is the bromine, is bonded to a different carbon. And then this is a functional isomer, and this has different functional groups. So this is like the example I showed earlier, which was the ethyl alcohol and the dimethyl ether. And it has this same chemical formula, but you can see that the functional groups are different. So like CH3 and CH2 versus CH3 and CH3 and an OH and an O. And then like you can see in this one, it's obviously drawn out differently, but this would be an example. So, okay, and then the other kind of isomer is a stereoisomer, also known as a geometric isomer. And there are two different kinds of those. There's an enantiomer, enantiomer, I don't know how to say that, but you know. And it is a mirror image of each other. So you can see these two are mirror images, and then it's chiral if its mirror image is not superimposable. So like these are superimposable. You could put this molecule, you could put on top of this molecule. But these two, which are mirror images of each other, you can't, like if you were to put them on top of each other, they don't match up. So it's like with your hands, if you go like this, they're mirror images. You can see this line dividing them, so they're mirror images, but if you try to put them on top of each other, they don't match up. So this one is an example of a chiral enantiomer. And then diastereomers, I should have practiced how to say these before I started this video, but diastereomers are not mirror images of each other. And then there are three like subgroups of those, I guess you'd say. So there is a cis, which has two groups are on the same side of the carbon bonds. And then trans, they're on opposite sides. So these, I'm sorry, these are labeled wrong, but this is a cis one because it's two on the same sides of this double carbon bond. And then this one is a trans because these are on opposite sides. And then conformers, they have different rotations. So like this one, you can see this, these two H's are going down like this. And then if you rotate it 60 degrees, it's the same, but these H's are like in a different place. So it like rotated it. So these are the same chemical formula, but rotated. And then these are the same chemical formula, but in a different structure. And then these are the same, but mirror images. And these are the same, but they're connected in different places. So you can see that. Okay, so that is stereoisomers, also known as geometric isomers. Okay, and then enantiomers, just a little bit more about them. So they can interact with plain polarized light, and they react differently with other chiral molecules than they would if it wasn't an enantiomer. And what makes a molecule chiral is these stereocenters, also known as a chiral center, and that's a carbon atom that's bonded in 4 different ways. So this picture, you see this is a little example of that. So we have this stereocenter right here, and it is, sorry, just lost my train of thought. It's bonded to this HO and this H, and then 2 carbons. And then this carbon is bonded to a carbon, a bromine, a CH3, and then another carbon. So you can see these two are different because they have different, they're bonded in 4 different ways. And this is not a chiral center because it is not bonded in 4 different ways. Okay. So that's how you can tell if a molecule is chiral or not. And then also keep in mind that chiral molecules are not superimposable. They're mirror images that are not superimposable. So keep that in mind as well. Okay, so I believe Dr. Mortensen also had this slide on his, what's it called? He also had this picture when he talked about isomers as well, but I thought it was really helpful. So I'm including it. So you can just see it like isomers. And then you either have a constitutional or a stereoisomer. And then the constitutional isomers are different. They like also divide up into 3 different groups based on the degree of branching. If it's a chain isomer, the position of the functional group, if it's a positional isomer, and the type of the functional group, if it's a functional isomer. So you can see these, like the chain, I think it was easiest for me to see with the chain isomer because this is obviously the same chemical formula, this one as this one, and the carbons are just bonded in different places. So like you can see in this one, this carbon is bonded to these, and then in this one, all the carbons are kind of like it's just different carbon skeleton, I guess is what you'd say. And then the positional isomer again is the functional group is changed positions. So see in this one, the functional group is over here, and in this one, the functional group, is over here. So different that way, and then different but the same, I guess. And then functional isomers, the type of functional group is different, which you can see in this as well, because in this one, you can see that they have different functional groups, but are obviously the same chemical formula. And then with stereoisomers, there are either enantiomers or diastereomers, however you pronounce that. There are 2 of those. So there's a non-superimposable mirror image, which you have right here. And those are also chiral, and they can't go on top of each other. And then conformers, and then in diastereomers, there's either cis, trans isomers, so cis, trans, and then the conformers, which are rotated, and that's how you tell. And you can see all of these have the same chemical formula, but different structures. So just really the most important thing to remember, isomers, same chemical formula, different structures, and then with each one of these, like just how you tell the difference between them. So for constitutional, which are structural isomers, you either have the chain, and the carbons are different, the positional and the functional group is different places, and then the type, and then the functional isomers and the type of functional group is different, and then the enantiomers, non-superimposable, so just think about hands, that's how I remember that. And then you have the cis trans isomers and the conformers. Okay, so moving on from that a little bit, we're gonna talk about fats, which is really exciting, yay, fats. Okay, so first you've got cis unsaturated fats. This right here, both of these are show cis unsaturated fats. So these ones are kinked, so they're bent. They have a lower density and a lower melting point because of the kink, because they can't stack as well because they're bent, so they don't go on top of each other very well, you know. So they're further apart, which because of those kinks makes them have the lower density and the lower melting point. These ones, the unsaturated fats, are the ones that are better for you. They're healthier for you. And then saturated fats, they have no kinks, which means they have a higher density and a higher melting point. So here's a saturated fat right here. And those ones stack better because, like, obviously they're flat, so they can go on top of each other. But that also means they're not as good for you because they can stick to your arteries, and that is not good. Don't want that. And then we have trans unsaturated fats. They have no kinks. They have a higher density and a higher melting point. And then because they're trans fats, they have these double bonds between the carbon atoms, which I'll talk about in the next slide, I believe. But that means that they're stronger. The stacks are stronger because of those double bonds. And this is showing those trans unsaturated fats. Okay, and then line structures, going on to these a little bit. So the lines, each of these lines represents a bond. The ends and the kinks are carbons. So like you can see in this would be the Lewis structure. You have each carbon written out and each hydrogen written out, and then this is the line structure. So each of these kinks and these ends, these are each a carbon. And then the H's are implied, and you can just remember that carbon has 4 bonds. So like you can see this carbon, for example, on the end has one, this carbon in the middle has 1, 2, 3, 4, and then this carbon in the middle has 1, 2, and then you can assume 2 hydrogens. So those are implied. And then you can see in this one also the double bonds are just represented by a double line. And then if you had a triple, it'd be like the same, like a triple line. And each of these is implied. But in this last one, you can see it also has an O on the end. And that you do have to write in because the kinks are the carbons and then the H's are implied. So if you don't write in these other atoms, then you'll assume that it's an H or a C. Okay. So hydrocarbons. What is a hydrocarbon? A hydrocarbon is a compound whose molecules are composed of hydrogen and carbon. Hydrocarbon, pretty simple to remember. And then there are 3 different types of hydrocarbons. So alkanes, which are also known as paraffins, they are molecules, they are hydrocarbons and all of the carbon bonds are single. So they're hydrocarbons whose carbon bonds are all single bonds. So you can see like here, this is a line structure, and all of these are single bonds. And then alkenes have 1 or more double bonds between their carbons. They're also unsaturated. And then the alkenes are saturated. So the alkenes, One or more double bonds between their carbons. So this one, you can see it has 1, 2, 3, 4 double bonds, but in order to be an alkene, it only needs one double bond between its carbons. So that's how you tell if it's an alkene, is if it has at least one double bond. And then an alkyne is a hydrocarbon with one or more triple bonds. So this would be an example of an alkyne because it has at least one triple bond. Then it would also be an alkyne if it had 2 triple bonds or 3 triple bonds or however many. So yeah, that's how you can tell what type of hydrocarbon it is based on the double and triple and single carbon bonds. And then talking about the double bonds, if you remember when we were talking about these trans unsaturated fats and these cis unsaturated fats, they both have a double, at least one double carbon bond. So they would be alkenes because of this. They each have at least one, and then this would be an alkane hydrocarbon. So obviously this double bond is going to make it even stronger, which we talked about a little bit when we were talking about the fats. So you just have to remember like the single bond alkane, and I'll go back to that slide. Single bond is an alkane, saturated. Double bond is an alkene, which is unsaturated, and then a triple bond is an alkyne, which is unsaturated as well. And the way that I like to remember that is, I don't really know. I just like think like, okay, alkane, A, first letter of the alphabet, so number one, so single bonds, and then alkenes. I just think it's, I don't really know, but I know the alkyne I remember because I just think this looks like a Y, and obviously not all alkynes are going to have this structure, but this is the picture that I picked because it looks like a Y and then it has a triple bond, and so that's how I remember like, okay, Y, that one picture of the structure of the line of the structure, like that one picture of that structure that looks like a Y and it has a triple bond, that's an alkyne. And then I just know the other one is an alkene, and that one, obviously, since we have A, one single bond, alkane, Y, alkyne, triple bond, then I think, okay, the only one left is the alkenes, and that one is the double bond. So basically, most important things, I think, to remember about this, or at least everything that I read about in those chapters at the beginning that was really emphasized, were the differences between these hydrocarbons. The fact that a hydrocarbon has to be a molecule of hydrogen and carbon atoms, which is pretty easy to remember. Just remember that these carbons are in, the ends and kinks are the carbons, and then you have to remember to about those implied hydrogens. Can't forget about those. And then fats, just remember about the kinks and what they do to each one. And then just the difference between these, each of these isomers is really important to remember as well. So with that, that is everything that I have to review about isomers. So thanks for watching. If you are watching, shout out to you. You're a real one. And yeah, good luck with everything. So thanks for watching this review about isomers. I hope you enjoyed. And I will now stop this recording.